This video is for lesson 1-6, the concept of proof. Axioms and definitions of words describe basic properties of the set of real numbers. From those basic properties, we can derive other properties of real numbers. Derived properties are called theorems, and theorems are proved to be true. So from those assumptions that we make at the beginning, we can create other ideas called theorems, which we can prove to be true. The first theorem we're going to discuss is the addition property of equality. If A, B, and C are real numbers and A equals B, then A plus C equals B plus C. This means that if you have an equation, you can add the same number to both sides of the equation and you will still have an equation. Let's prove that that's true. The format that you see on the video is called two-column proof. In the first column is a sequence of statements where the statements later in the sequence logically follow from what was written before. In the second column is justification for each statement. We have to be able to justify each statement in the logical sequence. We're going to assume that everything in the first half of the sentence is true because that's given to us. So it's copied down as the first statement, and the reason is given. Next, let's take a look at what we want to prove is true. Notice that the very last statement in the list is that information we're trying to prove. In between is our logical sequence of reasoning. All of the axioms that we've discussed are for real numbers, so we have to know for sure that everything mentioned in the theorem is a real number. We already know that A, B, and C are real numbers, but the theorem talks about adding A and C and adding B and C. So let's write down the reason we know that those are real numbers. Statement 2. Therefore, there is a real number D such that A plus C equals D. The reason we know that is the axiom of closure. That axiom said that when you add two real numbers, you're guaranteed to get another real number. This statement leads to statement 3, that B plus C equals D. How do we know that? Notice that this looks like the one written just before, except that the B has replaced the A, which is okay because earlier we knew that A equaled B. That's called substitution when you make a replacement like that. In the next step, notice that this statement has been switched around. The D is now on the left side and the B plus C is on the right. That can be done because of the symmetric property of equality. Next, we can logically take this statement and rewrite it into this statement. What's happening is that the A plus C is replacing the D. And that's okay because earlier we knew that A plus C was equal to D. So once again, that's substitution. In algebra, we use this theorem a lot. For example, let's solve this equation. You probably learned the following technique to solve an equation where a number was subtracted from m. You added that number to both sides of the equation. On the left side, the negative 18 and the plus 18 cancels out to 0, and on the right side, 2 plus 18 makes 20. The reason why it's okay to add 18 to both sides is because of the theorem we just proved. Next, let's look at the multiplication property of equality. If A, B, and C are real numbers and A equals B, then A times C equals B times C. This property says it's okay to multiply both sides of an equation by the same number. Let's prove that this is true. Notice the very first statement is the first half of the theorem that we're trying to prove. That's given to us. We're going to assume that that's all true. Next, we want to take a look at what we're trying to create. It has A times C and B times C. So we want to ensure that those are real numbers. So let's write this statement. Therefore, there is a real number D such that A times C equals D. The reason that we know A times C is a real number is because of the axiom of closure. If you multiply together two real numbers, you're guaranteed to get a real number. Next, we want to write down B times C equals D, but we have to justify writing that. Take a look at what we had right before. How can you get from this statement to this statement? What has happened? Notice that the letter B is replacing the letter A. And that's okay because earlier we knew that A equaled B. Which property was that? That's substitution. Now statement 4 is missing, but as a hint we're told we're going to use the symmetric property. So the symmetric property is when you take an equation and switch the sides. So our equation will be D equals B times C. If we know D equals B times C, we can conclude that AC equals BC. How do you get from this to this? Notice that the D is being replaced with the AC. Earlier we said that AC equaled D. So what's our reason? Substitution. This theorem is critical to algebra because it lets us solve another kind of equation. For example, solve 3x equals 24. The way that you learned to do this in algebra was to multiply both sides of the equation by the reciprocal of 3. 1/3 times 3 makes 1x, and 1/3 times 24 is 8. Let's take a look at another theorem. This one doesn't have a fancy name, but it's on page 19 of your book, so we'll refer to it as the page 19 theorem. If B and C are real numbers, then B plus C plus the opposite of C equals B. This probably makes common sense, but we can prove that this is true. Proofs always begin by writing down the given information, first part of the theorem. Next, take a look at what we're trying to prove. It has a B plus C in it and a negative C in it. We want to ensure that those are real numbers. So we'll make some statements to that effect and provide the justification. The sum of two real numbers is a real number because of the closure axiom. The opposite of a real number is a real number because of the axiom of additive inverses. Statement 4 is already filled in. When you add these two things together, the answer is a real number. Now it says given. Would you cross that out? That's a typo. The reason why we know that these two add together to make a real number is because of the closure axiom for addition. Once we've ensured that every numerical expression that appears in our theorem is a real number, we can start to think of what axioms that we learned about real numbers will allow us to prove that this is a true statement. Let's take statement 4 and create a logical progression of steps until we create what we're trying to prove is true. The first thing we could write is B plus C plus negative C is equal to B plus parenthesis C plus negative C. The reason we know this is true is the associative property. Next, focus on the c plus negative c part of that. What can you conclude about c plus negative c? It equals 0. Let's write that statement down. We know that adding opposites creates 0 because of the axiom of additive inverses. Next, let's combine that result from statement 6 with what we had earlier in statement 5. You'll notice that everything is identical to statement 5, except that that c plus negative c has been replaced by 0. Why can we do that? Because of substitution. Next, focus on the b plus 0 part. What can you conclude about b plus 0? It just equals b. Our justification is the axiom of 0. The axiom of 0 is the statement that adding 0 to any number gives you that same number. Now let's combine that result from number 8 with what we had earlier in number 7. Why is it okay to take the b plus 0 and replace it with just the b? That's substitution. Our last statement matches what we were trying to prove. Once a theorem is proved, it may be used as a justification in a proof for additional theorems, like in the next one. So this theorem has no fancy name, but it's on page 20 of the book, so we'll call it the page 20 theorem. If a, b, and c are real numbers, and a plus c equals b plus c, then we can conclude a equals b. Let's prove that that's actually true. The proof begins in the same way as all of the others. The first half of the sentence is copied down here and then later here, and our reason is given. The other thing we do at the start of a proof is ensure that all of the numerical expressions mentioned are real numbers. Besides a, b, and c, notice the expression a plus c and b plus c. So we want to make sure those are real numbers, and statement 2 takes care of that. We know that those make real numbers because of closure for addition. Next, negative c is never mentioned anywhere in the theorem. However, thinking ahead, I'm going to end up using negative c as an expression. So statement 3 takes care of proving that that is a real number. With all of that taken care of, let's figure out how we can get from statement 4 to what we're trying to prove, which is a equals b. Keep that in mind. We want it to look like a equals b. So one idea is to write a plus c plus negative c equals b plus c plus negative c. Why is it okay to add the same thing to both sides of the equation? Because the addition property of equality says you can. Next, focus on the left side of this statement. And as a hint, think about what the page 19 theorem was about. When you have an expression like this, this just equals a. Next, focus on this piece here. What does this equal to? It equals b, because of the page 19 theorem. Next, we can write A equals B, which is what we were trying to prove. Our reason is substitution. In place of this, we're putting A. And in place of this, we're putting B. Let's summarize the lesson. We discussed some theorems that will be useful to us in algebra this year. Theorems can be proved to be true. You write a sequence of logically connected statements and provide a reason for each statement.